Mathematics is the most beautiful and most powerful creation of the human spirit. A very good morning to one and all gathered here. Prayer is the opening of the heart to guide us to a friend. Prayer should always be our first response to every situation. So let us start today's session with Tamil Thai Valtu, followed by our college prayer.
கடலொடுத்த நிலமடந்தை கெழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
Dear participant, feedback link will be posted in the comment box at the end of the session. Now I request Mrs. Purnima Ma'am, Assistant Professor, Department of Mathematics with Computer Applications, to welcome our chief guest and participants.
A warm greeting to one and all. It gives me immense pleasure in welcoming you all to our national level webinar series, INFOQUEST on problem solving techniques, organized by the Department of Mathematics with Computer Applications, Dwarkadas Govindas Vaishnav College. I would like to place it on record the support and encouragement from the management of Dwarkadas Govindas Vaishnav College in organizing this webinar series. I would like to render my heartfelt gratitude to our Secretary, Sri Ashok Kumar Mungraji, Principal, Dr. S. Santosh Babu, for providing this opportunity. I also wholeheartedly thank the faculty members of the Department of Mathematics with Computer Applications for their enthusiastic support. It is a great privilege and honor to welcome our chief guest for the day, Dr. S. Viswanath, Professor, Department of Mathematics, the Institute of Mathematical Sciences, CIT Campus, Paramount, to deliver his lecture on the topic, problem-solving techniques. Thank you, sir, for accepting our invite. I make my cordial welcome to all the eminent teaching faculty, research scholars, and students of various institutions. Thank you for spending your valuable time and being here today. If your only tool is a hammer, then every problem looks like a nail. Problem solving is a highly sought after skill. There are many techniques to problem solving. Examples include trial and error, difference prediction, means end analysis, working backwards, and analogy. Some of the problem-solving techniques developed and used in philosophy, medicine, society, mathematics, engineering, computer science, and artificial intelligence in general are related to mental problem-solving techniques studied in psychology and cognitive sciences. Let us learn new methods of problem-solving from our speaker. We welcome you, sir. Now, I request Dr. P. Vijayalakshmi, Assistant Professor, Department of Mathematics with Computer Applications, to introduce our resource person. Thank you.
Good morning. Good morning to all. It is a moment of extreme pleasure to introduce our speaker, Dr. S. Viswanath, Professor, Department of Mathematics, the Institute of Mathematical Sciences, CIT Campus, Chennai. He accomplished his MSc Integrated Degree in Mathematics in IIT Kanpur in the year 1999 and his doctoral degree in University of California, Berkeley in 2004. He worked as a visiting research assistant professor, University of California, Davis from 2004 to 7, and as a lecturer in Pennsylvania State University, College Park 2007, and as assistant professor in IISc Bangalore from 2008 to 10. And he is also a reader in IMSc Chennai from 2010 to 13. And now he is a professor in the Institute of Mathematical Sciences Chennai from 2013 to till now. And his research interest is in Lie algebras and their representation, and also in algebraic combinatorics. He has published more than 25 articles in various reputed SCI index journals. Once again, I warmly welcome you, sir. The session is yours.
Thank you very much. So, let me share my screen. Is my screen visible?
No, sir.
No, sir.
Now it is visible,
No,
sir.
sir. Okay.
Yes.
Yeah. Okay. So, yeah. So, I'm, I titled it problem solving techniques. My goal is just to present maybe a handful of problems and sort of look at how they are solved, or what heuristic methods or what other methods we use in the background, just as guiding principles to try and solve it. Okay, so let me sort of start with the following question. So let's do the following. So let's look at the map of India. Okay, so sorry, this is getting used to this bit. Okay, so suppose I take the map of India, and so let's just look at sort of the southernmost and northernmost points maybe. So let me look at the north. Let me draw something up there as the northernmost extremity, something here which is the southernmost extremity. And so of course we sort of know the southern extremity, which is Kanyakumari. So here's, so let me mark, so on the India map, so here's Kanyakumari. Yes, I'm not going to try and draw the map. I was never particularly good at that. So here's let's say the northernmost point of India. Well, there's something I guess a little north of Leh, but for the purposes of this talk, let me just say it's Leh. Okay, so that's in Ladakh, of course, in Jammu and Kashmir. Well, I guess now it's a new union territory. So I have these two extremities, and of course, between these two ends, the entire country lies. And of course, one can think of these extremities, these lines that I drew, as the latitudes. Okay, so India is it's a country which lies entirely in the northern hemisphere. And if you sort of ask, well, what's the latitude of Kanyakumari? So that's around, so let me see, I wrote this down somewhere. So Kanyakumari is 8 degrees north latitude. So we are north of the equator. Kanyakumari is actually 8 degrees north of the equator. Okay. And let's see. So what's the northernmost point, which is, in my case, I said Leh, and Leh is around 34 degrees north latitude. Okay, so Chennai, I think, is around 13 degrees north. So this is 34 degrees north. So what I'm writing here are just the latitudes of the northernmost and southernmost points. Okay, so they lie between these two ends, 8 and 34 degree north latitudes. And of course, if you actually trace out a straight line between these two, so when I say straight line, I mean you sort of go along the longitude. Let's say you take the longitude on which Kanyakumari lies, and you sort of trace that longitude out. It's sort of remarkable. Actually, it goes through Leh more or less. I mean, it's not so important for what I'm going to say, but actually, it's interesting if you look at the map of India that Kanyakumari and Leh are actually almost the same longitude also. And in fact, that longitude which connects the two of them also passes through many other familiar places. So, for example, there's Delhi. Some parts of Delhi actually are at this longitude. So there's Delhi here. In fact, Bangalore is also on that same latitude. So more or less, they're all, all in a straight line in some sense. So Kanyakumari, Bangalore. There's also Bhopal, Agra, Delhi. Lots of them actually. So let's say there's Bhopal also. Okay, so now what I have is this straight line which connects the southern and northern parts of the country. I mean, two points in the southern and northernmost points. And of course, we sort of know how the weather is in all these places, right? So Kanyakumari today, well, I guess the rains have stopped to some extent. And according to Google Weather, it tells me Kanyakumari today is around 28, let's say 30 degrees centigrade. So here's the so I'm going to also note down on the other side the temperatures. Okay, so Kanyakumari is at 30 degrees centigrade. And Leh, of course, not surprisingly, up in the mountains, is actually minus 2 degrees centigrade today. Okay, so Leh is actually minus 2. So we are into December, so it's already winter there. Okay, so these are the temperatures. And of course, you can imagine that as you pass through these various cities, the temperature, well, it probably gets a bit colder as we move on. Delhi today is at 4 degrees centigrade. Okay, and I didn't quite look up Bangalore and Bhopal, but you can sort of imagine, right? So there is a variation. Starts at 30 degrees in Kanyakumari, and you get to minus 2 in Leh. It need not decrease necessarily the whole time. Meaning, of course, we imagine that as we go up north in the country, the temperature decreases. Need not always be like that. There could be some local effects. For example, Bangalore is sort of at an altitude, so Bangalore may suddenly be a bit colder than places which are slightly south of Bangalore, right? And so on. So temperature can vary in some funny fashion, but it sort of varies continuously. When you go from Kanyakumari to Leh, there's some continuous variation, maybe little up, little down, etc. And it reaches minus 2 degrees centigrade. Okay, now what I've done is this. I've actually noted down two interesting data points. One is the temperature, and the other is the latitude. Okay, so latitude is 34, temperature is minus 2. Okay, they measured in whatever centigrade here, and latitude is, of course, degrees north. So I got 8 and 30. Okay. Now, of course, I don't know anything in between. I don't know the temperatures of all the places in between. There are just far too many places. And in fact, the latitude passes through the entire country. I'm sorry, the longitude, for example, passes through the whole country. And of course, there are, not every point is necessarily a town or a city or a village. That can just be, uninhabited places, maybe forests and so on. So, but anyway, I think of every single point on this longitude, and every point has some temperature. Okay, so there's going to be some temperature. So the longitude varies from 8 to 34, and the temperature varies in some fashion. I don't know how, but continuously it goes from 30 to -2. Okay, so now here's the question that I sort of want to ask: is there a point, okay, in between these two, between 8 degrees north and 34 degrees north, somewhere on this line? Can I find a point? Where's my line? Okay, so I don't know where this point is going to be. Some point somewhere at which the longitude, the latitude value and the temperature value are the same. Okay, I want to know whether there is a point at some x degrees north longitude where today, right now, the temperature is x degrees centigrade. Okay. I hope my question is clear. So I want to ask, can I find a point where these two numbers are the same, the latitude of that point and the temperature of the point? Okay, so observe both Kanyakumari and Leh, of course, don't satisfy this property. In fact, neither does Delhi. I think Delhi is, let's see, what's the latitude of Delhi? 28 degrees. So Delhi happens to be at 28 degrees north latitude, latitude. So Delhi is 28. And it is 4 degrees. So this is 28 and 4. Right? This is so Delhi definitely doesn't satisfy this property. Latitude is 28 and temperature is 4. Leh is 34 and -2. Kanyakumari is 8 and 30. Okay, so these 3 points certainly don't satisfy this property. But my claim is, can I find some other point where these two numbers are the same? Okay. So here's an example of a problem, I suppose. So how does one, try and solve this problem, or how does one try and build some intuition on what, well, firstly, is there necessarily such a point? But maybe let me say, I give you the answer. There exists such a point necessarily. There must always be a point like this. Okay, and the goal is to try and prove it, or construct some plausible argument for why there must always be such a point. Okay, so how does one typically do things like this? So there's a key word that I mentioned, which is continuity. So I said that the temperature varies continuously. Okay, so let's just see what this continuous means. So this is one of our usual problem solving strategies, which is to try and draw a graph. Okay, drawing graphs has a nice thing that this notion of continuity and so on just is very intuitive. Continuity just means the graph of the function is going to be some continuous curve. So let's just see what let's try and record this information in some graphical format. Okay, so I'm just going to draw a line segment between, one end of which is Kanyakumari and the other end is Leh. Okay, just imagine this is my line segment. Now let me draw a graph. That is, I will note down for each point on this line, I will note down its longitude first, its latitude. Sorry, I keep switching the terms. What's the latitude of Kanyakumari? It starts at 8. And the latitude of Leh is 34. Okay, so I start what's the graph? If I plot on the y-axis, I plot the latitude of the point that's designated here. So if I do that, it goes something like this. So it's just a straight line, right? The latitude sort of varies continuously linearly as I go from Kanyakumari to Leh. So this is just a straight line graph between 8 and 34. Okay, so this is the latitude graph. So this is just what should we call it? Latitude. Okay, now let's try and do the same thing for the temperature. So what's the temperature at Kanyakumari? So put it in green. So temperature at Kanyakumari today we said was 30 degrees. So I'm going to draw it in the same scale. So this is 30 degrees here. Okay, and the temperature at Leh is -2. Okay, so Leh is -2. Now the point is, unlike the latitude, which sort of just varies linearly as I go from bottom to top, I don't know anything about the temperature. So as I said, the temperature could vary a little bit. Like I said, Bangalore is probably at an altitude, so suddenly the temperature drops and then rises again. Maybe again you reach some mountainous area, again maybe temperature drops locally a little bit, and so on. So the temperature is a funny graph. You don't quite know how it's going to be. All you know is that, well, two things. It starts at 30, it ends at -2, and it has to be something continuous. Okay. Now, if you sort of try to draw a graph which satisfies that condition, so you'll see you really don't have a choice. I mean, the temperature maybe when I first, so maybe this bottom is Bangalore, right? The temperature has gone down a little bit, temperature goes up again. Maybe I'm suddenly in the middle of the country where the temperature is very high. Suddenly close to Delhi, it starts dropping and so on. And then at some point it has to go to -2. And observe, because it has to go to -2, there's just no way out. It's got to somewhere cross that blue line. Okay, so the green line that I drew, I don't know the shape of the green line, but all I know is that it must go between 30 and -2, and it must be a continuous graph. Now, when that happens, there's just no option. It's got to intersect this blue line somewhere. Okay. Now, if you sort of see what that intersection point means, what is this point? Okay, so that's going to be some place in the country, right, between Kanyakumari and Leh. I've got some point. It may not be a city or a town, as I said. Nevertheless, it's some point in India on that same longitude. And this point P, whatever it is, if you look, what does this intersection mean? It just says that the blue line, the height of the blue line, that's just the latitude, is the same as the height of the green graph at that point, okay, which is the temperature. So this height, therefore, if you observe what this intersection of the two means, it just says that the latitude at P is the same as the temperature at P. In degrees, this is the temperature. And that's exactly what we were asking for. Is it always possible to find a point where these two things match? Okay, so this is sort of an instance of, there is a vast generalization of all this. There's a general framework in which this can be placed. So this is a property of continuous functions. So this is sometimes called the intermediate value property. If a function takes, for example, one way of stating is to say, if I have a continuous function which takes a positive value at some point and negative value at some other point, then between those two, it must take the value 0 somewhere. Yeah, that's one way of saying it. Okay, good. So, so this is an instance of this intermediate value property. Now, let's do this. Okay, now let me try and pose something which doesn't quite have the same feel, maybe, but okay. So let's start with this problem first. So suppose I oh, sorry. Okay. So suppose I do the following. So these are sometimes called cake cutting problems. So, well, actually, it's not a 3-dimensional cake. It's really a 2-dimensional problems related to 2-dimensional figures. So here's a geometric problem. So suppose I have a rectangle, okay, a rectangular cake, let's imagine. And now the question is, can you cut this cake into 2 equal pieces by drawing a horizontal line? Okay. So question is, can I make a horizontal cut and divide it into 2 equal pieces? And of course, we know that's possible. If it's a rectangular cake, all we have to do is just sort of divide this side length by 2, right? So you find the midpoint of this side, and then you place your knife there, right? You make the cut there. Of course, similarly, this sort of thing also works if your figure is symmetrical. Suppose I have a circular figure. Question is, can I divide it into 2 equal pieces by a horizontal cut, by horizontal line? Well, it's easy. You just take the horizontal diameter, right, the line passing through the center, that will cut it into 2 equal pieces. Okay, now the point, the question therefore, it is a generalization of all this, is to say, well, what if my cake was irregular? Suppose instead of these sort of specific pictures, was some strange flower-shaped cake. Okay, so here's my flower-shaped cake, and now my question is, can I cut this into 2 equal pieces by making a horizontal cut? Okay, so it's not anymore a straightforward question as before, because there is no obvious symmetry in this picture. Okay, so it's not as if you can find a line of symmetry which will allow you to conclude that the top and the bottom parts must have the same area. Okay, so in the absence of symmetry, does this question have a positive answer? Is it possible to cut it into 2 equal parts? Okay, so again, the answer turns out to be yes. It's always possible to do this. Okay. And again, to see why, let's just do the following. So let me just get rid of the line I drew. Now let's do the following. Suppose I ask, well, okay, I don't know where to cut. Okay, but maybe I should start by considering some extreme cases, some extreme possibilities. So what does that mean? So let me just do the following. Let me place my knife at the very bottom edge of this cake. Okay, so I'm going to try and cut this cake into 2 parts, but I'm going to do it in a very silly way. I'm going to just pick the bottommost point of this cake and cut it there. Okay, what do I mean by that? Well, that just means I'm cutting the cake into 2 pieces, where one of the pieces has area 0 and the other piece has area equal to the full area of the cake. Okay, so it's a very silly way of cutting the cake. If you cut it like this and give it to 2 children, one of them gets nothing, the other gets the whole cake. So that's one extreme situation. But let's do the following. Let's look at the other extreme situation, which is I cut it at the topmost point. So I make a horizontal cut like this at the topmost point. Now, when I do this, what am I doing? Well, I'm giving the first child the entire cake, and I'm giving the second child no cake at all. Okay, so this is the opposite of the earlier thing. Okay, and now how should I view this original problem? I should view it as follows. Imagine I move my knife, continuously between these 2 extremes. So just imagine that, I'm sort of trying all these possibilities. At the moment, I don't know if it's possible to cut into 2 equal pieces, but I can reframe my problem as follows. I know these 2 end or edge cases, and I can pose my problem as, can I continuously move my knife between this end to that end, such that at some point the 2 children get the same area. Okay, that they both get equal parts of the cake. Okay, so what do we know? Well, we know that in the starting point in this blue, when the knife is at the bottom edge, then child 1 gets nothing and child 2 gets the whole cake, right? So let's just tabulate what we have. So where is the knife? So let's just say knife, I put it at the bottom edge. Then what happens? Child 1, child 2. Okay, child 1 gets nothing. Child 2 gets the full area. Okay, the full cake. Then I move the knife to the other end. When it's at the top, child 1 gets everything and child 2 gets nothing. Okay, now when the cake is when the knife is moved continuously from here to here, what's going to happen? Well, this number is going to vary in some way from 0 to a, and the other number, of course, is just going to be, I mean, the total sum is constant. So the other, see, if this number is x, then that number is just a minus x. Right? So that's basically how it's going to vary. So here's again, so I mean, this problem doesn't look like the previous problem with Kanyakumari and Leh, but in some sense, it's actually secretly the same problem in disguise. Okay, so in what sense? So let's just let me draw a graph as follows. So I will say, okay, this is the cake being at the bottom. So actually, I don't need the vertical line here. Okay, so let's say this is the position when the knife is at the bottom end, and this is the position knife is at the top end. And what I'll plot on the other axis is what's the how much did the first child get. Okay, on the y-axis, it's enough to plot that. Okay, so I'm just going to plot the share that child 1 got. Okay. Now at the bottom end, child 1 got 0. At the top end, child 1 got the full area. Okay. Now, in between, I don't know how this area function varies, right? So all I know is that as I keep moving this knife further and further up, child 1 gets more and more cake. That's all. Okay. So in other words, it's some kind of increasing function. It increases in some fashion. I don't quite know how. It increases till finally the child 1 gets the entire cake. Okay. So this is how it varies. So I hope it's clear what I mean by this graph here. See, when I move my knife further and further up, how much extra will become the share of child 1? That I don't know. It doesn't vary in some regular fashion. See, if I was in a rectangular case, then it's easy to see. Every time I move a little bit, then the child, it'll be a linear function. Okay, so maybe this is a nice exercise in itself. As if it's a rectangle and I keep moving my knife further and further up, then child 1, the area that child 1 gets will vary linearly. Okay, now I mean, you can try and work out something similar for the circle as well, but more generally, if it is some strange figure like this, then it's not so clear how the area will vary. So it's some function, but again, the key word here, the operating principle, is that whatever it may be, we don't care. It's a continuous function. Okay, so this continuity is really what's important for us. Now, what is it that we wanted to prove? We wanted to say there exists a position of the knife at which the two halves have equal area. In other words, at some position, child 1 should get exactly a by 2 of the cake. So the claim is somewhere this child will get exactly a by 2. Okay, now what does that mean? So let's mark off a by 2 on our diagram. So we are saying if I draw this horizontal line here, a by 2, then this horizontal line will certainly meet this graph at some point. So if you sort of see, so firstly, it's clear that this horizontal line has to meet this graph. Okay, why is that? Because the graph is some continuous function. It's a graph of a continuous function. Between this graph, you can embed it inside this rectangular thing that I drew here. This outer thing is A. Okay, so this graph lives completely within this rectangle 0 to A on the vertical axis. And so when I draw the line a by 2, vertical length a by 2, then that must necessarily meet it at some point. Okay, so this is the same sort of argument we used before. So it meets it at some point means what? That is, look at the corresponding x-axis. that is some position of the knife between the bottom and the top. I don't know what it is, some strange position, some X position of the knife. Okay, so some X maybe. This is possibly the position of the knife. Okay, so there exists some position. I'm only trying to show existence, and there is some position at which the horizontal line a by 2 meets this graph, and observe that what that means is at that position child 1 gets exactly a by 2 of the cake. Okay, therefore child 2 also gets a by 2 of the cake. In other words, that's exactly the place at which the cake will be divided into 2 equal parts. Okay, so this is actually Kanyakumari and Leh, except with bottom and top. Okay, so this is really the same intermediate value theorem or principle. And again, here the problem solving. So I would say, just to, since it's supposed to be supposed to mention problem solving techniques in general. See, some of these. See, firstly, there is this thing that once you have solved many problems and you see a new unfamiliar problem, one of the things we try and do is to try and relate it to some problem we have solved before. Okay, even though it may not quite look the same, it has some features which remind you of that. Okay, so this is a bit like that. So if you have done these sorts of intermediate value problem theorem type problems, then anytime you see these sorts of continuously varying quantities between two possible values, you should always think of maybe some such argument is what is required. Now, the other thing that we are doing in all these cases, which is to sort of say, okay, I don't know whether it's possible to cut it equally, but let me at least study some edge cases. So this is sometimes the terminology we use. So we say, okay, can we study the edge case? Okay, what does edge case mean? It just means or extreme cases. Okay, so don't try to solve the original problem. Just say, okay, what if I take it to an extreme? Okay, what is the behavior at the extremes? And that's exactly what we're doing here. Okay, cut it in some very silly fashion by putting the knife at the very bottom. Okay, and then imagine what happens if I move the knife slowly to the top. Right? Once I reach the other edge, which is the top, then the behavior is different. So in between these two extremes, the behavior switches from one kind to the sort of the other end, to the other kind. Okay, where one child gets everything, and now here the other child gets everything. So somewhere in the middle, that competition will, because of continuity, will ensure that both children do get an equal amount. Okay, so this study of edge cases is always a very important thing to do. Okay. Fine. So moving on, the other principle that we often use is what we call generalization. Right. So if you solve a problem, so problem solving is actually maybe one. If you see a problem, if you're given a problem which you need to solve, and you've figured out how to solve it, often that's not the end of the story. So what you usually have to do is best for you to do is the following. You should ask yourself, okay, I used some idea to solve this problem. How much more can I get out of that idea? Okay? So that idea is often, useful to maybe solve something more, something extra, or something different. Okay, so that's what we usually call generalization, or studying the proof technique. That's the other term you can use for this. You used a certain method. The question is, how much more applicable is that method? Are there other problems to which that same method applies? So here's an instance of this. So suppose I say, okay, if I give you a strange shaped cake, okay, and now I say, okay, I don't want horizontal cut. I want to make a 30-degree cut. Okay, meaning, so let's imagine horizontal. I want to place the knife at a 30-degree angle. Okay, so somewhere I want to make parallel to this. Okay, so I want to cut it such that it makes a 30-degree angle to the horizontal. So can I cut it like this at this angle such that these two parts have the same area? Okay, so this is it's actually a different problem if you think about it, because the horizontal cut is a special sort of thing, right? See, I mean, this problem will it probably makes you wonder even in the rectangle case. Suppose I have a rectangle. Can you make a horizontal cut and divide a rectangle into two pieces? Yes, certainly. But can you make a 30-degree cut and divide a rectangle into two equal pieces? That's already a question. Right? That's not so obvious anymore, because the 30-degree line is not a line of symmetry for the rectangle. So the question is, can you still do this? Okay. And well, the answer is, yes. It's actually very simple now. Now that we have seen how to do the horizontal cut question. Why? Because this 30-degree cut doesn't really add anything new to our proof technique. So the same technique will work. So observe what was our technique. We said, okay, let's consider extreme cases. What if I make a 30-degree cut at this extreme? See, the extremes have changed, that's all. Instead of horizontal, when you make a horizontal cut, the extreme is the topmost and the bottommost point. Now it is sort of the point which is, when you imagine that you're moving the knife, this 30-degree knife, left and right, it's sort of the point, farthest point to the left where it meets, the farthest point on the right where it meets. Those are the two extreme cuts that you're going to look at. Okay, so these are the two edge cases now. Okay, so imagine, so this is the starting position of your knife. So starting position, this is your ending position. Okay, when you start, same thing, first child gets nothing, second child gets everything. Then you move the knife continuously. You imagine that you're moving the knife from this end to that end continuously. As you move the knife continuously, at the other end, the first child has gotten everything. Okay, so going from getting 0 to getting everything is what's happening to the first child. So by the same continuity argument, there must be some intermediate point at which the first child gets exactly a by 2 of the cake. So this always exists. Just the same continuity argument. Okay, and now the same argument works even for the rectangle. It doesn't matter what shape we have. So here's already a sort of a non-trivial thing that we have realized, that even if you don't have this line of symmetry, you take a rectangle, it's always possible to divide it into two equal parts by drawing, say, a 30-degree line. Okay, so this sort of thing is what you call generalization, or what you get by studying your proof technique a little bit more closely. And the point here is that there's nothing sacred about 30 degrees, right? So now, as you can see, I can make it any angle I want. So theta degrees, where theta is any angle, the same proof will work. Okay, so I can stipulate that I want to place my knife at an angle of theta, okay, and that I want to cut it into two equal parts by doing that. And is it possible? Yes. Why? The same proof works. Okay, so this is the generalization argument, that it's always possible because the same proof idea works. Okay, good. So now let's move on a little bit. So this is we looked at edge cases, we looked at generalization. This is in some sense as analogy, or maybe you say, okay, it reminds me of some earlier problem that I've solved. Now here's a slightly different sort of question. So this is more, not so much continuous, but rather more discrete. So here's the problem. So let me explain the problem statement first. So I'm going to do the following. I'm going to draw a chessboard. So this is a 8x8 chessboard. Okay, so I'm not drawing all the horizontal and vertical lines. So dot, 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 there are lots of lines there. So imagine I have an 8x8 chessboard. Okay, now here's what I do. So if you remember how a chessboard looks, there's some white squares and black squares, white squares and black squares, and so on. Oh, looks like I could just drawn the whole thing. 1, 2, 3, 4, 5. 4, 5, 6, 7, 8. Okay, and so on, right? So I draw these white and black squares. I mean, I actually have a chessboard. Now, here's the question. So what I want to do now is 5, 6, 7. Okay, so here's my chessboard. White. Okay, now what I'm going to do is the following. I'm going to look at, okay, so here's a piece. So this is sometimes what's called a tiling problem. Okay, so it's like these floor tiles that we lay on our floors. So what I'm going to do is I'm going to lay tiles, and all my tiles, so I'm going to place tiles on my chessboard. By a tile, I'll just mean my tiles all have the following shape. They are 2 cross 1 rectangles. So this is a rectangle with 2 boxes on this side and 1 box on this side. Okay, so this is my tile. Okay, so imagine I've got this floor, which is like a 8 cross 8 chessboard, big floor and square floor. And what I'm doing is I have some tiles. I've got these 2 cross 1 rectangular tiles, and the question is, can I tile this floor using this shape tiles? Okay, so I have many such tiles. I have as many as I want, and the question is, by laying these tiles next to each other, can I completely cover this floor? Okay, and of course the answer is, well, it's obviously yes. How do you tile a floor like this? You just, I lay the first tile here, I lay the second tile here. So here's one way of tiling it. I mean, there are many ways. You can either place it horizontally, vertically, etc. Next tile goes here, next tile goes here, etc. Right? Or I can do this guy vertically, this floor horizontally, one other fellow vertically, etc. So maybe there are many ways of doing it. Okay, but you can see it's definitely possible, for example, by just laying all the tiles horizontally. Okay, so that's going to cover this entire floor. Okay, so can we tile? Yes, that's clear, but that's not my question. So what I'm asking now, what I'm going to ask is the following, that see, I don't want this full chessboard. Okay, so I'm going to remove from this chessboard these last 2 parts, this corner and that corner. Okay, so I have a cupboard in my room, one cupboard in this end, one cupboard in the other end, and so of course those 2 parts are not, I don't want any tiles there. So it's a chessboard in which the last 2 ends have been removed. So I'm just removing the sorry, I'm removing these 2 bottom and top diagonal corners. Okay, so this cutout chessboard, the question now is, can we tile this chessboard? Okay, so this is not quite the same problem as before, because there is no obvious thing that we can do like we did last time. So let's see if we can do it with a different color. See, now there is one square missing here. So for example, if you attempt to tile it using horizontal pieces, so this, the trouble is now it's an odd number. So there is one additional guy here left over. So maybe then we have to make that vertical. There's no other option. Okay, so then we try this, but then again one fellow is left over. Okay, so I try this, make this vertical and so on. Now when you do this, you'll observe that at the very end, I will sort of run into trouble. I will have one additional thing there which I cannot fill. Okay, so if I try what I'm trying now, which is just keep putting it horizontal, except the very end alone, you try making it vertical. Okay, then you keep running into trouble. So maybe let's just do it very fast. So I do this, then I have to make it vertical, horizontal, 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 vertical. Okay, horizontal and then vertical. I'm already reaching close to the top, horizontal, 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 vertical, horizontal. Now I'm in trouble because observe that I should have put a vertical guy here, but then this particular thing is missing, right? So then I'm stuck. That one last square in that particular second last row, the second row from the top, that square is now, it's gotten missed out. I cannot tile it now. Okay, why? Because I can only use rectangular tiles 2x1, and the way I was trying to do it, by the time I reached that point, it turns out that that particular square is sort of unpaired. I cannot pair it with the guy next to it, and I can't put a vertical uh, tile there. Okay, so it seems like, well, all this says is that maybe I haven't been clever enough, that I have tried to give some way of doing it, but that way is not the correct way. Okay, but if you sort of try, and I sort of strongly recommend that you try various other ways of doing it. Change the horizontal and verticals. See if you could maybe start with horizontal here and then see if it works and so on. You will sort of conclude after you've tried this maybe for 10 or 15 minutes that it doesn't seem to be working. No matter what you do, there's just it just simply doesn't seem to work. Okay, so at the moment that's only a suspicion. Okay, because it just says that, well, I tried a lot, I tried to be very clever with different ways of tiling, but at the very end I still wasn't able to do it. Okay, but that's not a proof that it cannot be done. That's only something which points the needle of suspicion in the direction of the answer being no. So we start to suspect that the answer is no after we have tried it for a while. Okay, but that's still not a proof. That's an important thing. It could very well be that someone much cleverer than us could tell us tomorrow what the correct way of doing it is. Okay, maybe it's a very ingenious arrangement. Okay, but in this case, it turns out the answer is actually no. Okay, you can't do it. Okay, and let's say this problem was posed to you, that prove or again argue that this can never be done. Okay, so let me sort of point you to a very important argument here that we use in proofs like this. So this is sometimes what's called conservation principles. Okay, I'll come back to that terminology in a second. What do I mean by that here? So, okay, so what is happening? Let's think about it like that. So I said something about black and white. I needn't have said that in the beginning, because if I have this large 8x8 floor, I don't need to think of it as a chessboard, right? There's no blacks or whites. But it's actually better to think of this in terms of a chessboard, because it sort of gives us an idea for the proof. Okay, so imagine this was a chessboard. Then when I tile it, okay, when I place my 2x1 tile on this chessboard, what can happen? Only one of two things can happen, right? Either this left hand side, so what are the various ways of placing it? I can either place it horizontally or I can place it vertically on the chessboard. Okay, now when I place it horizontally, there are only two things that can happen. Either the square on the left was a black square, or the square on the right in the chessboard was black. Similarly, when I place it vertically, either the top square was black or the bottom square is black, right? Because my tile comprises two adjacent squares, One of the squares is always white, the other is always black. There's no choice, because that's the way the chessboard is colored anyway. Okay, good. So what does that mean? It says that suppose I had this sort of funny chessboard like this, right? And I tried to tile it. So I put one tile whichever way I wanted. Then the tile will surely cover one black and one white square. It need not have been like this. Maybe this was white and that is black. It's possible. But every time I put a tile, one black and one white square is gone. It accounts for that much. Okay, so each tile covers one white, one black. One white and one black square. Now let's see, the original chessboard has 64 squares, and out of which 32 are black and 32 are white. Right? This is the proper chessboard, would have had 32 black, 32 white. Okay, but then observe, this is a truncated chessboard. I've deleted this left bottom and right top diagonal edges, but actually both of them are white. Okay, so the way I've deleted two white squares from my chessboard. Okay, now since I've done that, this strange chessboard that I have actually has 32 black squares and 30 white squares. Okay, so that's actually already a very interesting observation, that we have done something very important. When we knocked out these two squares, we actually disturbed the balance between blacks and whites. Okay, so it became more blacks, 32 blacks and 30 whites, and now it is clear why you can never tile it by using these 2 cross 1 tiles, because no matter how you tile it, every time you place a tile, one white and one black square is being accounted for. Right? Now, in order to tile this chessboard, suppose it were possible, then how many tiles would I have needed? Observe, this chessboard now has only 62 squares. Okay, so therefore, out of in order to tile these 62 squares, I would have needed 31 tiles, because each tile covers 2 squares. But the tile covers one white and one black, and so if I had managed to tile it correctly, that means the resulting floor would needed to have 31 white and 31 black squares. But my original chessboard is not like that. It has 62 squares is okay, but it has 32 black and 30 white, as opposed to 31 white and 31 black. Okay, so therefore you can never tile it. Okay, so that's the proof, if you wish. Okay, so what is this terminology that I mentioned? What is this conservation principles? So observe, you can imagine that. So let me just say that there is a certain quantity that's conserved every time I tile it. Okay, what do we mean by that? See, the total number of black squares minus the total number of white squares. So if you take this original chessboard, I can define a new quantity if you wish. So let's call it E is the number of black minus the number of white squares. Okay, so that's the quantity E here. So to start with, the chessboard had 32 black and 30 white. So this number E is 2 when I start with the empty chessboard. Now imagine I do the following. I take this empty chessboard, I place one tile on it. Okay, I just place a tile, single tile. Okay, so I'm going to just remove this other tile which I drew. So I place a single tile on this chessboard. Now, once I do that, let's look at the remaining part of the chessboard. What's left to be tiled? So the remaining part of the chessboard, what's the value of E for that remaining portion? Okay, so the remaining chessboard, how many black squares and how many white squares will it have? Well, the original chessboard had 32 and 30, out of which one black and one white is gone, right? So the difference, so now it's 31 black and 29 white. The difference is still 2. So observe that after I place one tile, the value E for the remaining portion of the chessboard, the untiled portion, that's still 2. Okay, then I place one more tile. Okay. So I put one more tile somewhere and ask, okay, now that that part is also gone, what's the value of E for the remaining part, only for the remainder of the chessboard? Well, the answer is that's still 2. That still hasn't changed. Why? Because again, one black and one white has gone away. So, this number 2 never changes every time I do this. Okay. Now, when I keep tiling, at the very end, if I have managed to fully tile the chessboard, then the final value of E should be 0, because there is no more squares left, right? Number of blacks and whites should have been 0. But in this case, that can never happen, because every time you put one tile, the value of E still remains a 2. The value E never changes. So that's another way of rephrasing the argument that I already gave. So I called it E. Maybe you want to think of it as something like the energy of the chessboard, the untiled part of the chessboard. So you've probably seen things like this, conservation principles in physics, which is sort of the most natural place where they occur. So there is this law of conservation of energy, for example, the law of conservation of momentum, and so on. Now, what do these laws really say? They are actually, these conservation laws in physics are actually like this. So these are conservation laws. So you've probably seen energy, conservation of momentum, and so on. What it says is, well, I have some system, so it's got, there are no external forces acting on it and so on. So it's got some energy to start with. There are maybe many particles interacting in the system. Each of them has some energy, etc. There are, in the absence of external forces, see, the particles themselves may be interacting with each other, but when there is, and therefore each individual particle's energy may be changing. Okay, some of them are moving faster, slower, etc. But if there are no external forces acting on this system of particles, the total energy is always the same. Okay, so that's sort of like what we are doing here. It's saying when a process happens. Okay, so here again there is a process happening, which is particles sort of interact with each other. Maybe it's a collection of particles moving in a gas, molecules, and so on. So they interact with each other, and there is some process happening. There is some change in their maybe kinetic energies and so on. But in spite of what happens to the individual particles, the total energy, some quantity remains the same. Okay, so this is similar. Initially, I have a chessboard, or this strange, sorry, do it the other way around. So I have this strange chessboard whose total energy was 2. Okay, this chessboard's energy is 2, if you mean. I mean, just pretend I'm thinking of E as energy. Now, every time I tile it, I put a tile somewhere, energy doesn't change. Put a tile somewhere, still energy doesn't change. One more tile, still same energy. One more tile, still same energy, and so on. So what we are saying is, here is a process. So I'm now slowly changing my chessboard in some way by tiling it more and more. But this dynamical process, so sometimes we call it a dynamical system, dynamical process, and so on. I'm doing something to this system, which is tiling it more and more. But every time I tile it, this energy never changes. This number E never changes. Okay. And so what it means finally is that whatever configuration can be reached by this tiling, that whatever configuration you get, that fellow must have E equals 2. There is no other way out. Okay, so this is actually like a conservation law in physics. It's the same sort of thing, that no matter how these particles behave amongst themselves, finally the energy of the system must be a 2. Okay, if it started out with energy 2. Okay, good. So I'll just finish with one last example, which is sort of along the same lines, which again tells you something about conservation principles. So here's the problem. So you can think of it as some sort of a coin game, if you wish. So imagine I've got all the I have all the integers written on the plane, on the line 0, 1, -1, -2, 2, 3, 4, 5, and so on. Okay, I write down the entire list of integers, and now here's what I do. Okay, I place 4 coins on the plane, not on the plane, sorry, on the line. Okay, I place 4 coins at 1, 2, 3, and 4. So this is a starting configuration of my game. I'm going to play a game now with this. So what are the rules of the game? I can pick any 2 coins. Okay, take any 2 coins that you have. You move one of them k steps to the right. So that is I move it plus k steps and move the other minus k steps. In other words, one of them moves k steps to the right, the other fellow moves k steps to the left. Okay, and I keep playing this game again and again and again. So my repeat. Pick any 2 coins, move one of them k steps, move the other guy k steps to the left. So here is an example. Suppose I pick, let's say, the coins 2 and 3. So maybe I move 3 steps to the right, 3 goes to 6. So I place this coin at 6 and I delete this coin from here. But if I move 3 to 6, then I should move the other guy 3 steps to the left. So that 2 goes to -1. So I remove the coin from there, and I move it to -1. So this is my new configuration. Okay. So -1, 1, 4, and 6. That's where the 4 coins are. And I keep playing. Again, I pick any 2 of these. I can move them. And remember, this k is also anything I want. Okay. K is just any positive number. K is greater than or equal to 1. Any number, I don't care which number. But whatever you do, if you move one fellow k steps to the right, the other fellow must move k steps to the left. Okay, so and so on. So this is an infinite game. It can keep going on and on like this. You are allowed to put 2 coins on the same place also. I mean, if they both coincide on the same number, you put one on top of the other. You can keep one on top of the other if you wish. For example, I can take this coin 4 and put it on top of this coin at 6. That's allowed. Okay, which means I'm moving it 2 steps to the right. But when I do that, I should have taken some other coin and moved it 2 steps to the left. Okay, so that's those are the rules of my game. Very simple rules. Keep moving it again and again. And now the question is the following. So to start with, remember that the coins were equally spaced. They were at 1, 2, 3, and 4. This was the initial configuration of the 4 coins. Now my question is the following. By cleverly playing my game, by doing some number of moves, can I get these coins to be equally spaced with a spacing of 2? Okay, in other words, coin, nothing, coin, nothing, coin, nothing, and coin. So can I mean, I don't know. I'm not even saying I want them to be on certain integers. I just want the coins, instead of being spaced with a spacing of 1, I want them to be spaced out now with an equal spacing of 2 steps. Okay. So this is like saying, can I be clever enough? Again, it's a similar sort of question about tiling the chessboard and so on, which is, can I be clever enough and come up with some set of moves which will get me to this final configuration? Okay. So let me just quickly tell you the answer, because again, it's the same sort of conservation principle. So you observe that what's the thing that we are doing here? We are always moving one guy k steps and the other guy minus k steps. Okay, so this is a bit like conservation of energy, if you wish. So let's do the following. See, if the coins are at some configuration, if they are at some 4 places, x, y, or a, b, c, d, then I will define the energy to be the sum of those 4 numbers. Okay, so imagine I have a coin configuration like this. One of the coins is at the integer a, another is at b, another is at c, and another is at d. Okay, whichever those integers are, I will define the energy of this configuration to be the sum of those 4 integers. Okay. Now observe that this dynamical process. That is, every time I play my game, what happens? A, B, C, D has changed. It becomes some other 4 numbers, right? How does it become? I take one of these coins, maybe I chose B and C. B becomes B plus K. It's a new number, B prime. Okay. C becomes C prime, which is C minus K. The other 2 fellows, nothing happens. A and D remain where they are. Okay. Now, what's the new energy of this configuration? What's E prime? Well, it's a sum of these 4 numbers, but observe I added and subtracted a K. So this is actually the same as the original. This is still E, okay, which is A plus B plus C plus D. So what does this mean? Well, if I define energy like this as the sum of the 4 integers, then that energy is being conserved during this game. Okay, no matter how I play this game, the energy of my configuration is always going to be the same number as the initial value. And what was the initial value? The 4 coins were at 1, 2, 3, and 4. So the initial energy of this configuration of this, when I start the game, my initial energy is 1 plus 2 plus 3 plus 4, which is 10. Okay, this was my starting energy, if you wish. So, I mean, don't get too bogged down by my use of the word energy. It is not energy in any real sense. It's just some conserved quantity. It's a number which doesn't change, or it's a function, if you wish, of the configuration, which doesn't change as the game progresses. Same as what we did for the chessboard. Every time you put a tile, the number of black minus number of white, that didn't change. Okay, so there the game is you keep putting a tile, add one more tile. That's really the move there in that game. Here the move is what we have described. Okay, good. So now what was the question I asked? Okay, by playing the game cleverly, can I get the coins to be situated as follows? One of them is at X. The next fellow is at X plus 2. Right? I want spacing of 2. Next fellow is at X plus 4. The last coin is at X plus 6. Question is, can I get such a configuration? So let's see what's the energy of this configuration. This is, I add all these numbers, 4x plus 6 plus 4, 10 plus 2 is 12. Okay, so this is the total energy, which is 4x plus 12. And I know that the energy is conserved, right? So I know for sure that this number must actually equal 10. That much I'm sure of. Okay, what does that tell me? It tells me that 4x equals minus 2, or x is minus half. Okay, now observe that's not possible because x is supposed to be an integer, right? The coins are to be placed on integral points, on integers. So of course this is a meaningless answer. This can't happen. Right? So what that tells you is that this is not possible. It's not possible to place my 4 coins in such a way that they all have equal spacing. Okay, good. So this is another instance of a conservation. Okay, I guess I'm out of time more or less. So maybe I'd like to stop here. Thank you.
No problem, sir. Okay, sir. I think no questions, sir. No queries, sir.
Okay, sure. Thanks.
It's the time for vote of thanks. On behalf of the Department of Mathematics with the computer applications and organizers, I'm very happy to express my sincere gratitude to our eminent speaker, Dr. S. Viswanath, Professor, Department of Mathematics, the Institute of Mathematical Sciences, CIT Campus, Theramani, for grace us with his valuable talk and problem-solving technique. Really, it is a remarkable session for us, sir. Once again, I thank you very much for your very interesting and provoking talk to learn the concept, sir. Thank you so much for your presentation, sir. And I would like to thank our beloved secretary, Sri Ashok Kumar Mundraji, and our principal, Dr. S. Santosh Babu, sir. I would also like to thank our beloved HOD, Mrs. B. Sangeeta, ma'am. Thank you, ma'am. Thank you so much for your moral support and guidance. And my heartfelt thank for all our staff members and scholars. Teachers can open the door, but you must enter it yourself. Last but not the least, our beloved participants for making this function as a grand success. Once again, I thank one and all present here. Thank you so much for all.